Okay, so we have been looking at triple integrals, and triple integrals, of course, we can do triple integrals with rectangular coordinates. We can do triple integrals with cylindrical coordinates. We can do triple integrals with spherical coordinates. And naturally, one coordinate system is usually advantageous over the other coordinate systems. So in this problem, we want to find the volume of a solid that lies above this cone, given by z equals the square root of plus x squared, z equals the positive square root of x squared plus y squared, and then the volume that's above that cone but below this sphere. So let me give you a moment to copy the example down, and let's look at this example. Okay. Okay, so this sphere has equation x squared plus y squared plus z squared equals z. Is that sphere centered at the origin? Do you think that sphere is centered at the origin? Well, let's think on this. Let's think a little bit about this. If you had as an example, if you had x squared plus y squared plus z squared equals 9. Okay, where would that sphere be centered? Where would the center of that sphere be? We know 9 equals 3 squared, so the sphere has a radius of 3, but where would it be centered? That's right, Logan. That's right, Alexander. It would be centered at the origin, right? Because really, you can think of this sphere as, x minus 0 squared plus y minus 0 squared plus z minus 0 squared, and that equals 9. But here you have a variable on the right side. And if you were to move it to the left side, you would have x squared plus y squared. Let me just clear this here, one moment. You can think of this sphere as x squared plus y squared plus z squared minus z equals 0. And so that is not a sphere centered at the origin. It can't be because of the minus z. So this is a sphere that's not centered at the origin, and of course, it would be helpful to understand where the sphere is centered at. Now, I know you have a problem in your homework that's like this, and they'll say, for instance, like in this case, the sphere is centered at 0, 0, and a half, and they just say it without stating why. But I think probably you can figure that out why. But I'm going to just show you here. So let's get an idea of of what this solid looks like that lies above this cone and below this sphere. And also we recognize that for volume with a triple integral, it's a triple integral 1 with a 1 as the integrand dv over some solid E. So the dv here is decided when you choose either rectangular, cylindrical, or spherical coordinates. The fact that we have a sphere involved here, okay, in this problem, could be an indicator that maybe spherical coordinates would be the way to go. So, okay, let's go to the next page. All right, you notice that I've drawn a picture here. I've drawn a picture where I have a sphere. Hold on here, it keeps catching. All right, I have a sphere centered at 0, 0, a half. So the sphere, I'm saying, has a center of 0, 0, and a half. How do we, so again, the solid is bounded above by the sphere and below by this cone, right? By that cone there. But how do we know the sphere is centered at 0, 0, and a half? Well, we have to take the equation of the sphere and re-express it. So remember, how many remember completing the square? Yeah, that's right. That's what we're doing here. Yeva remembers that. And Ashriha remembers that. Wonderful, wonderful. So this part here is z squared minus z. That's like z squared minus 1z. And there's a 1 in front of z squared. So what you do, the rule is you take the negative 1, the coefficient of z, divide it by 2, and square it. And that's going to give you a fourth in this case. So you're going to have to add a fourth, like I'm doing here, to the left side. But then I'm going to add a fourth to the right side as well because I have an equation here, right? But z squared minus 1z plus a fourth then is the same as z minus 1/2 quantity squared. And you see you can therefore now you're able to write this equation of a sphere in standard form, and the center is 0, 0, and a half. I mean, you've done this before with circles, for instance, in two-dimensional space, where you complete the square to figure out what the center is. We're just doing it with a circle in three-dimensional space. The center is going to be 0, 0, and a half, and the radius, well, is going to be the square root of that 1/4 there. And so the radius equals a half. So now we have our sphere. Here it is. And we have to decide what coordinate system to use. And I'm suggesting let's try using spherical coordinates. Now, we did a problem before where we used cylindrical coordinates. That was helpful for our triple integral. Here I'm suggesting spherical coordinates. So for spherical coordinates, what we have to do is the solid is formed by the cone below, and the sphere above. And naturally, the region D that is involved then, in other words, we have a surface above, which is the sphere, and a surface below, which is the cone. If we're going to use spherical coordinates, we have to express those surfaces as spherical coordinates. So what I do is x squared plus y squared plus z squared equals z. Well, x squared plus y squared plus z squared equals rho squared, according to this, spherical coordinates. And z is rho cosine phi. So therefore, rho squared equals rho cosine phi. And if I divide by rho, okay, we're assuming rho is, basically positive, right? Rho would equal cosine phi. And that's the solid over the surface above. Are there any questions so far? All right, now things are going to work a little differently, by the way, when we get to the triple integral, because the triple integral for spherical coordinates, we need limits for rho and for our angles phi and theta. But certainly, it's critical to figure out. Well, I want to say this the right way. So, in terms of your limits for rho, okay, I'm just gonna. So you see here the dashed that line there, dashed line. Any point. Okay, any point. Let me make this 3 point, if I may. Any point in this solid would have a rho that starts at 0, and the largest value of rho would be rho times the cosine of phi, because rho cosine of phi describes the sphere, and that's like the boundary. That's the boundary. So your limits on rho are going to go from rho equals 0 to rho equals cosine phi. But now what we have to do is we have to get limits for phi. Well, of course, a point here, phi would equal 0. Okay, but the phi values start at phi equals 0, and they go all the way to where the cone is. Well, what's the equation of the cone? Well, the equation of the cone is phi equals pi over 4. Okay, how do we get that though? Well, all right. So here's the equation of the cone, z equals the square root of x squared plus y squared. I substitute in z equals rho cosine phi, and then I substitute the definite x and y. Okay, and I do a little bit of mathematics. I factor out the rho squared sine squared phi, common to both terms under the square root, and I end up getting rho cosine phi equals rho sine of phi. That's what I end up getting. Please let me know if you have any questions. I tried to put a lot of detail in the work here. But if I take rho cosine of phi, and it equals rho sine of phi, okay, that's a little bit, let me, hold on, I got to do my little eraser. thing, but I know how to do it now. I know how to really do it great now. Let's try this again. So, okay, rho cosine of phi equals rho sine of phi. If I divide both sides by cosine of phi, by rho cosine of phi, rho cosine of phi, I'm going to get then 1 equals the tangent of phi. And incidentally, rho cosine of phi will not equal 0 because, you know, for cosine of phi to equal 0, phi would have to be 90 degrees. And this solid never reaches 90 degrees, right? It never reaches 90 degrees. So 1 equals the tangent of phi, but then phi equals pi over 4. And so now that the cone in spherical coordinates can be expressed as phi equals pi over 4, and therefore the limits on phi would range from 0 to pi over 4. See how that works? Okay, let me give you a little time just to copy if you need it. Please let me know if you have any questions. Who's feeling comfortable so far? Okay, Simon is good. Yeva is very good. Ashvia, Aaron, Norina, very good. Thank you. Matthew. So there's a little bit of work involved in getting the limits, but you're going to find it's tremendously helpful in computing this volume. Computing this volume using rectangular coordinates would it would be well, I haven't worked it out, but it would be harder than using spherical coordinates. Let's put it that way. I'm glad we're seeing good participation today. Sometimes what I do is I reach out to people, you know, who are maybe they're logged in and but not responding, and then, you know, they kind of, okay, let me get the, you know. So I'm very happy that you're participating, and excellent. And all right. So here we go. So now the volume of the solid is given by this triple integral. dV, as you know, using spherical coordinates, it has the dV is rho squared sine of phi d rho d phi d theta. Now you could do rho squared sine of phi d rho d theta d phi. Okay, you can change the order, but generally I like to save my theta for last. And based on that solid that we had, rho, all coordinates on that solid, their rho values would have to go between 0 and cosine of phi. And the phi values for any spherical coordinate on that solid would have to be between 0 and pi over 4. And the theta would naturally go between 0 and 2 pi. And so you have a very nice integral here to work with. So naturally, I like to do the iteration. I like to use that, the iteration symbols here. I'm going to integrate with the rho squared sine of phi with respect to rho first. And that means, in this case, you treat the angle phi as a constant for that inner integral. The antiderivative of rho squared is rho cubed over 3. Okay, and so now you put in your limits. And this is the kind of work I would want to see on your 4th exam. And you get down to here. So please let me know if you have any questions up to there. So this is really now the second iteration. I have an integral with respect to phi. And really, it's like a calculus 2 problem. I'm going to do substitution, right? I'm going to let u equal cosine phi, and then it'll turn out, when you work it out, that sine phi d phi equals negative du. And so that second integral will well, the new limits would go from 1 to square root of 2 over 2. How are we getting 1? Well, 1 is equal to the cosine of 0. Remember, the bottom phi limit is 0. And then root 2, and now the top phi limit is pi over 4. So because u is the cosine of phi, the new u limit corresponding to pi over 4 would be the cosine of pi over 4, and that's square root of 2 over 2. So with these triple integrals, integration, I mean, there are problems where the integration can get quite complicated, but I think for the problems you're going to be doing, the integration should be pretty straightforward. Ashifa asks, during exams, Ashifa, you are not allowed to look at past web-assigned homework questions during the actual exam, because it's an exam. So that's a good question. And in the special instructions that are there listed with the exam, the proctor was incorrect on that. Thank you for bringing that to my attention, Ashifa. Yeah, the special special instructions are like that, you have access to be able to see, do state that on exams you're not supposed to be looking at past homework problems and so forth. I mean, you're taking the exam just like you were taking it in a classroom, and it's closed notes, closed homework, right? Like we're in a classroom. So, but I do let you access the ebook. You are allowed to access the ebook. And the reason I do that is because there are formulas that sometimes students need. Like, for instance, here you notice you needed to remember, for instance, that that the unit of volume for spherical coordinates is rho squared sine phi d rho d phi d theta. And if you don't know that, you're not going to get the problem right. And any engineer would have access to that, you know. So I think it's just I think it's reasonable that, hey, if you can access the ebook, just so for those instances where you forget those little things, you can then probably you have them. Most students do have them correctly memorized, but they might want to just double check. How many maybe have done that occasionally on a test? Just sort of double check that kind of thing. I'm sure students have. Okay, Yeva has, for instance. Okay, sure. Or like, for instance, like a trig identity. If there's a trig identity you need in order to complete your integration, and you forget that, you know, sine squared of theta, if you forget that sine, hold on, I have it here. One moment. Yeah, if you forget that sine squared of theta equals 1 minus cosine of 2 theta divided by 2, you know, I don't want you to miss the problem because you couldn't remember that trig identity. So in the ebook, you have the trig identities are located in Appendix C in the end matter in the ebook. So, you know, that's fine. Any engineer would have access to those formulas. Okay, so good question. Now we proceed on. We now integrate with respect to u. Now you'll notice here that you have a minus in front of that du. And if we were to absorb the minus, it would cause those limits, those inner limits, to flip. So here there's a minus in front of the negative du. But if I remove the minus, then the limits flip from root 2 over 2 to 1. How many kind of like to do that in an integration sometimes? Like to absorb the negative and flip the limits? Or how many remember that from Calculus 2 learning, or Calculus 1, that's about that? Sure, Norina remembers that. And yeah, so, you know, and then you just proceed forward. And, you know, the antiderivative of u cubed is equal to u to the 4th over 4. And we substitute in the 1 and the root 2 over 2. It's really quite beautiful. And the antiderivative of 1/16 is 1/16 theta. And in the end, you're going to get an answer of pi over 8. That's the volume of that ice cream cone, the exact volume. So for instance, if you're a company and you're creating like snow cones, we've seen snow cones, they have that shape of that solid that I showed for this problem. You know, you want to know the exact volume of product you're going to use to make the snow cone. You don't want to, you know, be guessing. You want to have the exact volume. So if it's pi over 8, I don't know, cubic inches or whatever, you know, that's important because you can efficiently and correctly compute the cost it would make to produce snow cones, because you know the exact volume of the ice cream needed. You know, a lot of times with food, margins are kind of tight, you know, on food products. So exact computations are critical. Was this a good problem? How many kind of like this problem? That found this to be kind of a nice, just a nice problem to do to help reinforce some of the concepts in section 12.8. Okay, Christopher's liking it. Excellent. Norina, wonderful. And Matthew, good. And Samuel, great. All right. Are there any questions before I, let me just solve. So our, one moment. Okay, so our ice cream cone here, the volume is equal to pi over 8, which is like about 3.14 divided by 8. But that's the volume. Okay. All right, I will stop the recording then. Very good.